higher scientific concept between students and teachers. And it is essential to bring in the local languages as far as possible. And we are trying to make an effort. But when this actually becomes reality, we don't know. So we have made an attempt in that direction also. So today we are having a distinguished speaker, Professor Rajaram Nityananda from ICTS-TIFR. We are very thankful to him and welcome him to this particular program. And he will speak about the topic phases of entropy. So before he speaks for about 15 minutes, followed by 10 minutes of question and answer session, I request our General Secretary, Professor P. Nagaraju, to introduce the speaker briefly. Over to you, Nagaraju.
Yes, sir. Namaskara, sir. Elrigu. So it is my pleasure to introduce Professor Rajaram Nityananda. Of course, he studied physics at the Vivekananda College and IIT Chennai, and joined Professor S. Ramasheshan at the National Aeronautical Laboratory, Bangalore, for a PhD program in 1969. He got his PhD in the topic Optics and Crystallography from Bangalore University. He joined RRI in 1975 and worked there for over 25 years. He worked in the areas of condensed matter physics, astronomical optics, image processing, and gravitational dynamics. He served as director of NCRA, National Center of Radio Astrophysics, TIFR, from 2000 to 2010. He has taught physics and astronomy at the PhD students in Bangalore, Pune, TIFR Hyderabad, and ISAR Pune. He taught at Azim Premji University from 2014 to 2021. He was visiting professor at ICTS, International Center for Theoretical Sciences, TIFR, 2022 to 25, and currently continuing as senior faculty associate. He is a fellow of 3 Indian Science Academies. And what are the 3 Indian Academies? Let's expand them. Indian Academy of Sciences, Bangalore, and the Indian National Science Academy. The other one is the National Academy of Sciences. So he is a fellow of all the 3 sciences, Indian Academy of Sciences. And he is the chief editor of Pramana, Journal of Astrophysics and Astronomy and Resonance. He is also teaching basic physics and astronomy to young students and wider audience. With a brief introduction, I request Professor Rajaram Nityananda to give his talk. Thank you very much, sir, for accepting our invitation. It is a great honor to our Karnataka Physics Association. Sir, please proceed for your talk. Thank you.
Thank you, Dr. Nagaraju. And I just want to make a small correction. I used to be the chief editor of many of these journals many years ago, but now, of course, they have much younger and more active chief editors. And it's also nice, of course, even many of the people from Bangalore University I have encountered in the past. Dr. Kagari will remember, in fact. And it's nice to see people whom I used to know in RRI, like Uday, of course, and Srikanta, whom I have not seen for a long time. Okay, so this is a very old topic, right? I'm using the word thermal physics to include both our thermodynamics, which is very traditional calorimetry, this, that, temperature, so on. But I would like to, as we go along, tell you that it's been an active subject and things have happened not just in 1850 and so on, where thermodynamics was established, but right up to the present time, very interesting work is being done in this area. I don't have to say this is important for technology. If one is teaching a class, I'm sure half your class would have come on some kind of two-wheeler, which is really a heat engine of some kind. Nowadays, one worries a lot about energy, environment, sustainability. And if you go deeper into any of these issues, you find that you have to understand and apply concepts from thermodynamics. What is maybe a little more surprising is that this concept of entropy, which is there in the title, has a connection with communication and computation. And I will try and bring that out toward the end of the talk. So the unifying concept is entropy, which is why it's there in the title. Now I thought, this was really targeted at I don't know if any students are in the audience, but perhaps even for the teachers, you want to make students relate to things in their everyday life. So, of course, I was taught in calories, but nowadays we have to speak in megajoules. So even if you buy something, the energy content will be given in megajoules. So 1 liter of petrol, which again, now this may surprise you, a good solid meal is only 2 megajoules. So it actually tells you that for energy-wise, petrol is cheaper than, right? Yeah, than food. Okay. Now, of course, we all get electricity bills, which are in kilowatt hours, depending, of course, some people get it free, but if one is paying the standard rate, it will be about 10 rupees, right? Now, this is a very important topic, cooking gas, right? And especially at the current time. So I've given this number, but it's important that this is not just the weight of the gas. So the gas is able to take in oxygen from the surroundings, and it's the combination which releases so much energy. But if you send a rocket, then you have to carry your oxygen with you, right? So interestingly, the number is about the same as cooking gas, but of course, the rocket fuel is able to come out with a large velocity, which is what is important. But what I would like to look at this number, which is of course less than all the numbers we have seen, right? Everything's in the range of 30 and so on. But if you take a kg of gas molecules in air at room temperature, and you ask how much is their energy, it's about 1 megajoule per kilogram. Not very much. But if you could really extract this energy, there's a huge supply of air. So that would be very useful, right? And this would be a kind of dream that you take air and you extract the energy of kinetic energy. So of course the kinetic energy becomes less and the waste product would be liquid air. But then you just send the liquid air out and the sun will heat it up anyway. And this would be a fantastic solution to everything, right? But we know that this is not possible, okay? And this is where this great man, and repeatedly we'll encounter people who are actually engineers, not necessarily people who came in with the physics motivation. So Carnot, early 19th century, he realized that there is an obstacle, okay? And we'll be talking more about it, okay? So it just because, whatever we described earlier doesn't violate conservation of energy. You're removing energy and the air gets colder and so the total energy remains the same. But there is a further obstacle. And this is what, of course, we're going to talk about. Carnot realized there's an obstacle and it is Clausius. Anyway, I just put down the second law of, he put down both the laws of thermodynamics in a single German sentence. That is, the energy of the world is constant, but the entropy tends towards a maximum. But it was mysterious, okay? And that mystery was removed to a large extent by later in the same 19th century by Boltzmann. So 1 kg of liquid air is more orderly than 1 kg of gaseous air, right? Now, what has this got to do with things? What it really means is, it's not that easy to go from a disorderly state to an orderly state. You're all familiar with this. You have various things in your homes. Maybe many of you keep things very neatly in your homes, but sometimes, or some people, they scatter things around. And then if you're looking for something, you cannot find it. Or if you just squeeze the toothpaste out of a tube, putting it back in is more difficult. So really, there are irreversible processes. And the key thing is to understand that. So I've just chosen one example. This is not a full course, right? So the one example is a container of air which is split into 2 halves, and there are 2 possibilities. You can fill 1 half with air and keep the other half empty. Or, and you can make a hole in that partition and then it fills the whole air container. And then our common experience tells us that if you just wait, you will not find all the air going back to one half of the room, which is just as well because we all need to breathe. Okay. And simple-minded, I mean, if one has to introduce students to this in the simplest possible way, you think of a gas molecule having a choice of being on the left or right, like heads and tails of a coin. Okay. So whatever we have in the second figure, the whole container filled, is like a configuration where roughly half are heads and half are tails. It's not a single configuration, that's the crucial point. I've shown you HTTH in some order, but so long as half of them are H and half of them are T, that's fine. But the first case is where everything is heads, right? So that's very rare. Now, when I was teaching in Azim University, I could see that my class was getting a bit restless, so I took them out, okay? And then we played the following game. We had a little open space. We divided into two parts, and every person's name was written on a piece of paper. And the idea was to simulate the random motion of molecules, okay? So one person would take a slip and call out. And whoever's name is called out will move from whichever side they are to the opposite side. So you start with all the people on one side. Naturally, whichever slip you took, the person will move. Now let's say majority are still on the left side. It is still possible that you may call a person on the right side to go back. So that would be a situation where the total number of molecules on the left is increasing and on the right is decreasing. But you carry out the experiment, it becomes pretty clear that it settles down to roughly equal. Now the roughly is important. Let's say we had an even number, okay? I mean, maybe there were 30 students in the class, 15 and 15. But it's not that the same 15 are sitting on this side or on that side. Because the process continues, the random process, like molecular collisions. You keep calling out names. But people, now that there are equal numbers on both sides, it's equally likely that people go from left to right or right to left. So on the average, this remains as it is. But I think the on the average is important. The equality is not strict. It will fluctuate. Okay. So very briefly, because this is standard textbook material, the thermodynamic entropy, we go through this whole thing on heat engines. And maybe one way of stating it is that this heat added divided by temperature, right? Now it's something, I mean, you may be able to remove heat from some source of heat, but then this quantity will either increase in the working substance of the engine or the same, it may compensate, okay? But it's like a karma, you cannot get rid of it, right? You can create it, you can transfer it, but you cannot destroy it, okay? It's there. And of course, this was purely in the basis of heat engines. By the way, since I said faces of entropy, you'll see a lot of faces of these scientists here. So he realized that this is not peculiar to heat engines. So he thought of a reversible process in which you add heat. And in this case, the entropy remains constant, okay? So whatever is removed from one place reappears in another place. But later on, we will talk about irreversible processes where this quantity actually increases. So anyway, that's the standard textbook material. Now, I'm not sure, certainly in my own bachelor's, statistical part was not at all taught, but perhaps it is taught nowadays. In some sense, he removed the mystery, and the only mystery is why he used a symbol W for the number of ways of achieving a given state, and it's German for probability, okay? And I already anticipated this in the coin toss example, where if you want equal number of heads and tails, it can be achieved in many ways, but if you want only heads, it can be achieved only in one way, okay? But what is interesting is that, taking the example of a gas with collisions, he was actually able to give a mathematical proof that this W increase is with time. I have put proved in quotes because actually this was slightly controversial. We will see why. Now, the Boltzmann's work was great, it was a breakthrough, but it didn't touch upon many of the systems which people are interested in, which are not gases. Okay, it could be liquids, solids, and so on. So the person who was able to extend Boltzmann's ideas is Gibbs. It's also interesting because he was in the United States, which was at that time there was hardly any physics going on in the United States. So almost in isolation, he seems to have developed all these ideas, but not completely in isolation because he actually traveled for a few years to Europe and he attended various lectures and so on. So this is a somewhat more abstract approach. So I will just touch upon it because we do teach it usually only at the master's level. So the word phase now refers to some space, mathematical space, where you look at all the positions and all the velocities of all the particles. So it's a very high dimensional space. And he generalized the concept to the volume. Extension is his old-fashioned word for volume in the space. Okay? But he also introduced this interesting idea called ensemble. And you are interested in a specific system. You have prepared it and you're interested in it. But if you want to understand the properties of that system, he suggested that you don't look at that system alone. You look at similar systems which have been prepared in a similar way, and look at that whole collection, and you try to describe the average. Okay. Now, I just went to the dictionary. The word is used in fashion for a number of items of dress which are coordinated. It could be a group of actors. I mean, Uday will be very familiar with that. And but the way Gibbs used it, it's a fictitious collection of systems. I'm just emphasizing the word fictitious because we only have one system in the lab, but we calculate averages over this whole collection. And there are different ensembles depending on the conditions. Are you at constant temperature? Is the system isolated? Maybe the system particles are coming in and out. Okay. And actually, it requires a lot of thought and discussion to see why this approach works. But if you think about it, we use this all the time. Okay, it's really a way of coping with your ignorance of the system. Okay, and we'll come back to this theme. So you cannot predict what an individual coin will do, but you can make better predictions if there are 1,000 coins being tossed, right? So the real thing to appreciate is this idea. And interestingly, Gibbs was already toward the end of his life, at the turn of the 20th century, entering the 20th century. And Einstein, of course, we all know about his work on photoelectric effect and relativity. But in the same year, he gave his PhD thesis where he explained this phenomenon of Brownian motion. You have small particles, but big enough to be seen. So they're not individual molecules. They have millions of atoms in it. And they were seen to move all the time. Okay? So he had this brilliant idea that take that Boltzmann's formula, which relates entropy to probability, but turn it around. And you see the probability of finding a given state depends on its entropy. So now, earlier one said the entropy was maximum because that is the most probable state. But if you just toss 10 coins, you will not get 5 and 5. You may get 4 and 6. And in fact, when I did an experiment in the class, a few people even got, well, maybe not 10, but they got 8 and 2. Okay? So the deeper picture of a system, and it's especially important for a small system with not a large number of molecules, the system keeps fluctuating. So the second law has to be understood in this sense. There is a state, the most probable state, but the system, because of its own fluctuations, will occasionally explore states which have lower probability. And the state with the lowest probability is the state with the lowest entropy. Okay. So that is how you have this individual Brownian particle. It collides with the surrounding molecules. And of course, if you only looked at those collisions, it would go on gaining energy. But that's not what happens, because at a given temperature, this particle is governed by the idea of equipartition energy. It will have energy corresponding to k by t. So actually its velocity will be much less, because if you say half mv square is k by t, if m is large, right, a massive particle, velocity will be rather small, okay? But, so on the average, its velocity has to settle down, on the average. So how does this happen? The collisions keep increasing its speed, but if it moves too fast, there is a friction from the surrounding. And these two have to balance and ensure that this particle has the right amount, its fair share of energy, of Boltzmann's constant unit temperature. So Einstein used this argument to derive this relation which I have written down below. It's not a question, I'm not interested in deriving it, but I can tell you what's going on. So mu is really a measure of friction. If you apply a certain force, how much velocity will it pick up? Okay. But d is a measure of random motion, that is diffusion. And he was the first to realize, or one of the first few people, that there is this connection between the two and the absolute temperature. Okay. So that is Einstein, right? But meanwhile, as I said, there was skepticism about the derivations which Boltzmann had given, because if you mechanics, after all, the whole business of collisions between molecules is governed by mechanics. Now, mechanics has an interesting property. If you imagine taking a film of some molecules colliding with each other and exchanging energy and so on, if you run the film backwards, that will also obey the laws of mechanics. And the mathematical reason is that they contain the second derivative with respect to time, Newton's laws, right? So you change t to minus t. So at the level of individual molecules, things seem to be reversible. But now Boltzmann seems to have proved that things are irreversible, right? System will go to a maximum entropy state. So these two were reconciled by a person whose name we don't usually give in thermodynamics. So that's why I have put him down here. He's called Ehrenfest. So he had the following picture, and this picture has, at that time, this was also controversial. But today there is no doubt about it, because today one can actually put, a large number of molecules, maybe even thousands, in a box, in a computer, let them collide, and keep track of the entropy. As I said, a very simple measure of entropy would be the difference between the left and right halves of a container, but take any measure of entropy. So this is the maximum entropy state. So just like the game which I described to you, most of the time you'll be in a state which is close to that. But every now and then, and it's really a matter of luck, right? These random collisions, you may suddenly find that so think of this vertical axis as measuring the difference between, absolute value of the difference between number of molecules in the left and right. So most of the time they are nearly equal, this is zero. But then, you get a large difference and so on. Now the important property of this curve is that the large fluctuations are much rarer than the small fluctuations. So then how do we understand Boltzmann's derivation? So the idea is, take a system with any value of the entropy you like. So it could be here, it could be here, it could be here. But because this one is so rare, it's unlikely to be here. Okay. Actually, I'm giving my cursor. Not sure it's visible on your side. It's not, no?
No, you can see.
Oh, you can see the
visible,
cursor.
Rajaram.
Visible, yeah, visible.
Oh, very nice.
For me, it's
Okay.
visible. Yeah.
Okay, good. Sometimes it doesn't show. So if you prepare a system in a state with a lower entropy, like everything in the left half of the container, most likely it will be near a peak of this curve. Of course, it could be a part of this. So then this is the case, a rare case, where you have prepared the system here, and then the difference in number of molecules keeps increasing. But this is very rare. So the more likely thing is that you have caught this at its maximum excursion, because these are the most probable fluctuations. So I used to explain this again to lighten up the class by imagining that you have all these autos from Majestic, and let's say each auto driver is prepared to go a certain distance. There are some people who will only go, maybe up to Malleshwaram. Some people may want to go up to Rajajinagar. Very few will go up to Yelahanka and so on. So if you live in Yelahanka, you will not see these guys at all.
No.
But most likely you will see the person who has just come to Yelahanka and is prepared to go back. Okay? Because the people who will be are prepared to go even further than Yelahanka are very rare. Okay? So I like this auto driver analogy that at a given, say, auto stand, you will find the people who always want to go to Majestic. So you think it's irreversible that you're manufacturing autos and they're all going to Majestic. But that's not true. It's just that small fluctuations are common and large fluctuations are rare. Now, this idea of Einstein of relating fluctuations to transport phenomena was taken further by this person. He is again a legend in statistical physics. His name is Onsager. And the standard example which is given is, he, of course, it may look like a very small generalization. See, if we put an electric field in a metal, you get an electric current. If you put a temperature gradient, you get a heat flow. But actually, these two are related. I mean, in the sense, an electric field may produce a heat current, and a temperature difference may produce voltage differences, and so on. So, when you talk of these irreversible processes, you are sometimes talking of coupling in many variables. So, he generalized this argument, right? And he was able to explain certain laws which are already known, you know. But what is interesting is that this work won the Nobel Prize many, many years later, because it became very important to chemists and so on. Onsager himself, of course, continued his work in statistical physics. If you talk to any person, they'll tell you that the Nobel Prize has been given for his most minor contribution. He's done even bigger contributions. In fact, the legend is that he received the phone call, picked up by his wife, and they say, "Oh, your husband has received the Nobel Prize." So she's still sleepy. She asks, "Is it for physics or chemistry?" And actually, it turned out it was for chemistry because it was useful. But of course, he has done fantastic things in physics, which I will stay away from. Now, this is a person who again won the Nobel Prize, but he decided to push in a different direction. And he was in Belgium, so he and his Gharana are called the Brussels School. So, I hope it's not my phone. Is it? Okay. Yeah, okay. Now, he took something which is convection. You heat a liquid from below, and heat flows, and it's removed from the top. Okay? But what happens if you keep increasing the temperature gradient is you start developing some structures. You develop cells. And this is a famous demonstration experiment. So it looks like some order is emerging. But of course, if you keep track of the entropy, you're not violating the second law. But the states of such a system, which is being driven from the outside, can show order. And this is very important because otherwise we have a fundamental problem. In the 19th century, people were always worried that according to the second law, everything is going to reach equilibrium, temperature will become constant, density will become constant, chemical composition will become constant. And this was called the heat depth of the universe. Okay? But people like Prigozhin realized that this heat depth is not true. In fact, you will get order in part of the system, and of course, the entropy will all be pushed into the rest of the system. In fact, our whole Earth is a bit like that. It receives energy from the sun. Right? We use it in various ways, but ultimately, the Earth has to get rid of just like the Carnot engine. It needs to radiate to a sink. Okay? And one of the biggest worries is that if you fill the atmosphere with carbon dioxide, the Earth cannot radiate away that energy very efficiently. And these ideas are especially important in astronomy and cosmology, because here in cosmology, we tell our students that the universe started out very uniform in temperature, almost uniform in density, and so on. How is it now that we have planets and so on? And there again, the gravitational force has a tendency to create disorder without violating the second law. I think that's the crucial point. Now, before leaving this theme of fluctuations, I want to tell you that even toward the late 20th century, people came back to this subject. And the motivation was that now experimental skills using laser tweezers and so on, people were able to study very small systems. Okay, but they were interested in applying thermodynamics. So I can see if one wants the equation of state of a gas with lots of molecules, you can push it to the piston. Or if you want the equation of state of some elastic solid, you may be able to apply some stresses to it, look at the strain and so on. But if you pull a DNA molecule, based on everything that I have told you, you will not get the same result every time. Okay? Because it's surrounded by this bath, which is random. And the smaller the molecule is, the more it's affected by these random processes. So can one still get useful information from these? So this is a person called Jarzynski, and he actually came up with this very nice. I will not be able to go into detail, but I would still like to point to this relationship. If you remove that bar, the left-hand side, and remove the exponential, then it simply tells you something that is well known, that the work done is related to the change in free energy from the initial state and final state. Okay. But now, when you pull this DNA molecule, you repeat the experiment, every time you get a different value of W. Okay. But if you, and then the correct thing to average, according to this equation, is you should average this exponential minus W by kBT. Okay. And then that will tell you the free energy difference between the molecule, let us say, before you pulled it and after you pulled it. Now this is interesting because this is a experiment where neither the initial state nor the final state is well defined, right? You start pulling the molecule at a certain temperature at a certain length, but there are many configurations of the molecule, and you have, that's why you have to take this average. And a few years later, a deeper reason, which is really related to this Ehrenfest argument, was given by a person called Gavin Crooks. The reason why I brought up these two people is their work is relatively recent, and therefore, you know, unless one specializes in this field, one may not have. But also to make the point that these old concepts like work, free energy, and so on have now acquired new meaning when you work with very small systems. And of course, one field in which people are pushing towards smaller and smaller systems is semiconductors. And I remember how astonished I used to be many years ago when I read that people are now making wires which are 45 nanometers in diameter. I said, my God, this is a little bit. Now today, I think the technology is some 5 nanometers or something. So as you go to these smaller and smaller systems, you have to look at this randomness. So this is the more fundamental result, on the basis of which, after averaging, you can derive this. Of course, this is the one which is useful to experimenters. Whereas, if you want to derive it, you look at the probability of fluctuating from A to B and fluctuating from B to A. This is somewhat related to what I told you about this Ehrenfest argument. Okay? So I'm just putting this up as an example of current research. People are still working on multiple examples of this. Now I would actually go backwards. And of course, Maxwell is well known for his Maxwell equations, but he also gave you the Maxwell distribution. Okay. Sorry? Yeah. So he was interested in the kinetic theory of gases, but he suddenly had this doubt about the second law of thermodynamics. Okay. So he created this demon. So again, a container with two halves, equal number of molecules on both sides, and a hole. But now there is some kind of gatekeeper who decides that only fast molecules will be allowed from left to right, and slow molecules will be allowed from right to left. So numbers may remain the same, but the temperatures will now develop. And he himself never gave an answer as to whether this was really possible. Okay. So this remained a kind of nagging doubt about the second law of thermodynamics, whether a system with the help of this demon could actually violate the second law of thermodynamics. Now Szilard is again a physicist who is more well known for his contributions to atom bomb and so on. But before he did all that, he came up with this idea. He said, let's have a heat engine, a Carnot engine. So it has a hot wall, and molecules can bump into the wall and pick up energy. And then they bump into this piston and push it. Okay? Now that itself is not a heat engine. An engine has to be cyclic. You have to get things back to the original state and get back. In the Carnot engine, you get rid of some of the heat so that the gas comes to a lower temperature, and then you push the piston back. So that you have to do work in that step, but the net amount of energy you have extracted is equal to the difference of the heat which you took from here and you put out in the sink. That's the Carnot engine. But the Szilard engine is different. The molecule picks up energy from the hot wall and bounces off this piston, pushes it, some work is done. Now, he just waits. When someone gives you the information that the molecule is on the left half, you quickly move the partition here. That's why I have drawn this line. You don't have to do any work because the molecule is not bouncing off here. Okay. So that's what I've explained. You do not remove heat, right? But so now of course, Szilard and others who thought about this problem did believe in the second law of thermodynamics. So they tried to analyze how will you get this information. Okay, maybe that process itself will be equivalent to a heat sink, whether it will be equivalent to so that the entropy itself is conserved. Okay. Now this is where I want to make a small digression. So here is another engineer, Shannon, who worked for Bell Telephone Labs, and he was entirely concerned with making telephones more efficient. But he developed a mathematical theory of communication, and I think this is a very nice idea. I hope I'm not. Yeah. So he actually is not dealing with thermodynamics, dealing with people who exchange messages. So does the message carry any information? And the answer is only if you were ignorant of the contents before receiving the message. So if I tell you the sun will rise tomorrow, that's not really useful information. But I'll give you an example where there is actually information, right? So if you agree that the ignorance of the recipient can be measured by the number of alternatives, right? Before we receive the message. Then, of course, one of the alternatives is realized when you receive the message, and now your knowledge, your ignorance has, of course, come to zero. Okay? So the value of the information you have received can be measured by W. In simple cases. So, so Shannon's definition of entropy, in fact, he's, I think, the person who also introduced the term bit for binary digit. So in simple cases, if the message has, some H number of bits, okay, then W is 2 raised to H, or H is log of W to the base 2. Now, of course, Boltzmann used base E, but it's very easy to convert from base E to base 2. That's not a problem. So, this is for the case of equal probability, which is the only one that we need to talk about. It can also be generalized for unequal probability. So, if you send a message with letters of the English alphabet, then they are not equally probable. And also they are not uncorrelated. Usually a Q is followed by a U, but not always. Right? If it's the Bangladesh cricket team, many people's names end with a Q, but there's no U following it. Okay? So, without actually giving you the details, I'm telling you that Shannon gave a definition of information based on this W, which includes cases where the probabilities are not equal or and the different events may be correlated. Okay. So this is my elementary example, okay. And this actually happened to me, right? Many years ago, more than 40 years ago, I was in Phenomena, and this is, we did not take any ultrasound. So when this lady came out holding a bundle, W was 2. And it has 2 possible answers, right? So it's 1 bit of information. Of course, she said it's a girl, and then I got that 1 bit of information. Now, of course, at the same time in Phenomena, there were many of these maternity wards, and 6 nurses came out and with 6 bundles, and there were 6 anxious husbands around. Now, you could say W is 64, But it seems reasonable to say that you would like to add the information, because the same thing is happening in all the wards. So that's the reason. This is to justify why we take the log. So this is 6 bits of information. Okay. I want to emphasize that this is before all the modern ultrasound and so on, where W is 1 even before the child is born. Okay. Now, I come to more engineers, people working in IBM. Well, they may not be engineers, because IBM would also hire very good physicists. These are 2 names. Again, their work is very much late 20th century. They said that this information is actually physical, right? It's not just some abstract thing. So, the argument of Bennett was the following. Let's say you keep, every time, somehow he gets the information. So he writes down a 1 or a 0, depending on whether the molecule is in the left half or the right half. And you gather 1 bit. Now remember our original condition for a true heat engine, that the process must be completely cyclic. And earlier I said, okay, the piston has come back, therefore it's cyclic. But that's not completely true. So the point made by these gentlemen is that you have written down all these bits. Okay? So what happens to your memory, right? When you are writing down these bits? So ultimately you have to erase the memory, and only then the cycle is complete. Right? And in fact, all computers are irreversible. If they were not irreversible, then as you went on using the computer, all the possible computations you did are all sitting there. But we all know computers get hot. Okay? So this is a very interesting connection between computation and irreversibility. Okay? And but so that also means that if you actually take even physical devices like memory cells, or you have to analyze them with physics. And it's not enough to say it has to stay 0 and 1. You have to ask, how do you maintain it? What's the probability of, there could be fluctuations, right? And you don't want it to be. You want a 0 to remain a 0, a 1 to remain a 1. Now, I was very shocked when many years ago I heard that Bitcoin consumed more electricity than the whole of Greece. But now I'm told that data centers for AI will consume even more than that. So people are thinking of putting them in space or putting them undersea so that they get cold. So this is, I don't know, I mean, this is frightening. But so I would just like to make the point that every time you do a Google search, or of course if you use an AI, of course here nothing, everything seems fine. You get an instant answer, but somewhere, you know, something is getting heated up. Maybe some coal is being burnt. So my last example is from fundamental physics and from astronomy, and this has to do with black holes. So at some point, Bekenstein, who was a research student at that point in the US, realized that there is, and his guide, who was Wheeler, said, if I just keep, putting things into a black hole, right? That's the perfect sink for any heat engine. Okay. So then you may not actually be violating the second law, but then you have to associate some entropy with this black hole. Right? But can the black hole take an infinite amount of heat from your heat engine? Remember, problem faced by Carnot was how to get rid of the heat, right? Not all of it, but get rid of some so that you can push the piston back. So, so he wrote down a formula, and ultimately it's Hawking who took up the thing. And the entropy of black hole, I'm just writing down a formula, it's in units of Boltzmann's constant. So if I remove that kb, it's dimensionless. So it's half the area, but area has to be measured in certain units. And remember, this is a quantum process now, which we are talking about. Huh? So it has the gravitation, because black holes involve gravity, has Planck's constant, And of course, there is no other relativity. So there is this quantity called Planck length. So interestingly, long before all these theories came, the moment Planck discovered Planck's constant, he realized with G, H bar and C, I can construct a length. And this length is really very small. It's 10 minus 33 centimeters, something like that. So that means A is really very large when you make it dimensionless. So a solar mass black hole has an entropy of 10 raised to 76. You can work out, not difficult. And this is interesting because the sun itself, you think it's very hot and it should have a very high entropy. But its entropy is only 10 raised to 58 in these same units. So surprisingly, if you collapse the sun to a very small radius of 3 kilometers and it becomes a black hole, its entropy increases by an enormous amount. And today we know that the universe is filled with black holes. In the galactic center, all over our galaxy, other galaxies. Right? But now what happens to Boltzmann? We know that you have to associate this entropy with a black hole, otherwise your second law will be in trouble. Okay? If you are getting rid of entropy from the surroundings of the black hole, then the entropy of the black hole must be increasing. But what are the microstates? And of course, this has to involve quantum mechanics, right? So, if you believe this formula, and everyone believes it, the major entropy in the universe is actually in black holes, not in data centers or, heat engines or anything else. But what W is there are ideas, but I would still say there is no final answer. If you want the best answer, you should probably call someone from ICTS who works in string theory or related areas. And they might introduce you to what are the models for the microstates of black holes, right? So I would like to, I hope I've brought you all the way to much more recent developments. And this was obviously like a very hurried tour, like these bus operators who will take you from here to Halbit Belur, Shravanam, Bedagola, etc., bring you back late on that night. But then later on, one can go and explore any of these things at leisure if you want. So thank you very much.
Thank you very much, Professor, for a very nice talk. Now there's time available for questions. Anybody who would like to ask a question, you may raise your digital hand and then ask. Anyone? You can start with any questions on this topic. So I was wondering myself, the formation of life, does it violate the entropy principle? Because it's creating more order out of disorder. Life formation.
It is creating order locally.
Yeah.
But
there is a compensating thing.
There is a compensating thing. And maybe the best proof of that may happen if we don't allow heat to escape from the earth. Right? See, heat escaping from the earth obviously carries away entropy, right? I mean, entropy is increasing somewhere else.
Yeah.
So if you take even a biological system and you isolate it, it will die. If you don't allow it to get rid of the waste products, either chemical waste products or thermal waste products, it will die. So, of course, it's still not trivial. All you're saying, it doesn't violate. There is compensating elsewhere, but it's still interesting to know the mechanism. And that is exactly where people like Prigozhin made their reputation. They actually were able to identify a mechanism where this order emerges, at the same time, of course, creating disorder elsewhere. So, for example, the simplest example of convection, in fact, we see that. I mean, even this morning when I was boiling the milk, right? You see some nice patterns developing. But remember, you're heating the milk from below and the heat is going away from the top. So, as I said, this is not a good answer. In fact, there's an interesting case where a professor was asked by his student, you say that I can always reverse a process provided I can compensate elsewhere. Okay? So, the student asks, how do you unfry an egg? So the professor says, go and feed it to a hen. So compensation is important, but mechanism is important, and that is why biophysicists like Vijay Kumar, Krishnamurthy and so on, they would like to know the mechanism whereby this order emerges. mean, through experiments, computer simulations, and theory.
We'll go on to the next question. Professor
No.
Keshavamurthy,
Yes,
please
sir.
ask.
Yeah, this entropy is always something which occupies the minds of lots of people.
Yes.
In fact, I was always wondering, it was also paradoxical to think that order can be created in the universe in the form of formation of stars, black holes, and then we all have this heat death of the universe. So to reconcile the two, I thought now only I know that it requires quantum mechanics. Would that be, would there be some philosophical implications, or can we guess the age of the universe by accurately estimating the way in which entropy is changing in time?
Okay. So first of all, the heat death was very much a concept of the 19th century. And it's true that if we were all living in a box, sooner or later this heat death would have occurred.
Yeah.
So, however, gravity changes the situation quite a bit. So, one thing which I did not mention, suppose you have air in a room or something. I said that the uniform state has the highest entropy. But actually, if it is a very huge room, then the system can increase its entropy by some of the mass going on one side, okay? But because of gravity, that mass continues to be held on that side. And again, because of that, its temperature increases, okay? So, you mentioned star formation. So, star formation occurs through this kind of instability, that you may start with a uniform medium, but a small amount of excess mass gathers more and more mass around it, and then it gets hotter and hotter. So, this gravitational instability does not violate second law, but it does violate the uniformity of the universe. But even that, if the universe was, I think ultimately it's the expansion of the universe which seems to create conditions whereby you have this, stars, planets occupying a very small fraction of the volume and large amount of empty space in between. So yes, I think ultimately many people have written that second law has to be connected to cosmology. If we lived in a different kind of universe, maybe we'll be seeing something different.
Okay, now
What would be the role of these quantum fluctuations in that case?
Well, in the current understanding, see, I'm not an expert on that, but in cosmology, this initial non-uniformity, which later on gives rise to stars and galaxies, is supposed to come from quantum fluctuations. It's the so-called theory of inflation, where you start with quantum fluctuations, and that is something you cannot get rid of. It's a minimal fluctuation that any system will have. And then people in various models try to show that as the universe expands, these quantum fluctuations will grow. So that they definitely have a role in theory. Of course, one has to test this theory through observations, and a lot of people are trying to do that.
move on to the next question. Nitin, would you like to ask a question? Please go ahead.
Hello, Professor. This is related to biophysics. From thermodynamics, we have one definition of entropy. From statistical mechanics, we have another definition. We have EEG signals which analyze, which characterize the brain waves. Is there a way to classify or characterize the EEG signal in terms of entropy?
Yes, and there I think what the electrical engineers do, the Shannon kind of entropy would be the appropriate measure. That is, one has to have a large collection of EEG signals, and then one, by looking at the various correlations of the voltage in those signals, one can compute an entropy. One can compute the Shannon entropy, in fact. So I would say the appropriate thing in applications like EEG signals and all that, and of course, could be other applications in biophysics also. Like there is chemical communication going on and so on. So in general, see, we say a signal is random, but it's not fully random, right? I mean, there is some element of predictability.
Yes.
If you show me a small part of the signal, I can make some statement about what it might do in the next second, but I cannot say what will be 1 hour from now. So it's autocorrelation or whatever has some finite extent. So yes, I would say that entropy is associated. And I think Shannon even has a formula giving the entropy in terms of the power spectrum of the signal or autocorrelation.
Okay.
Any other questions? I heard about this atoms of space and time with regard to explaining the entropy of black holes. Could you say something about that? What are the
Completely not my area, but yeah. As I said, living in ICTS, I hear only the string version.
yeah, the string version?
I mean, and I said, I mean here, which is not the same as understand.
Yeah,
But I hear it from my colleagues.
yeah.
Yes, there are other models in which space-time is, consists of some discrete
Discrete bodies.
elements. In fact, there is people working on that in the Raman Institute, like Madhavan Varadarajan, Sumati Surya. They work on a non-string
Wow.
approach to quantum gravity. So,
Okay. Any other questions? So the we ask.
Yeah. So no, it's not a question that you mentioned, Professor. You mentioned about Professor Ehrenfest as well as Boltzmann and Ehrenfest. Was Ehrenfest a student of Boltzmann?
Actually, I think so. I remember looking it up once. Initial exposure, I'm not sure it was directly Boltzmann. Of course, he ultimately worked in Netherlands, and Boltzmann was based in Austria. But in those days, people did move around. So I think there was a direct influence. Of course, you probably know the tragic story that both of them.
They both committed suicide and
but maybe for
and
personal
so
reasons.
committed to the subject. I don't know how much of the subject. I mean, that they were so passionate about the subject that they were doing.
See, in Boltzmann's case, it is true that there was a lot of criticism based on this reversibility and so on. But I think there were also personal or health reasons in both cases.
Thank you. I mean, I just wanted to.
Okay, we move on to next question by Professor Malesh. Please ask.
Good morning, sir. Nice talk for you. Nice talk, Professor Nityananda. I have two questions. I wanted to kindly one. Again, elaborate on how reversible entropy refers to more disorder than this maximum occupation. That's my.
Okay, 3 slides. He says it increases on the average. So you're averaging between an ensemble of systems. Okay. Now, what is interesting is it doesn't contradict reversibility because take this standard example of gas filling a container. You set up some initial conditions in a computer simulation and you find it fills the container. Same initial conditions, you reverse the velocities, again it will fill the container. And this is only possible if the particular state which you are starting with is near a minimum of that curve which I showed you. So whether you run it in one direction or the other direction, the entropy increases. So that's the simple reconciliation of reversibility and also realizing that it really refers to average behavior. Right? You can always imagine systems which violate the second law of thermodynamics, but the question is how do you prepare them and how rare are they? So for example, a system, the gas might fill the whole container. If I reverse all the velocities, it should go back and fill. But can you really reverse all the velocities of, that would require a huge amount of information and so on, which gets related to the other concept of information being a physical entity. It's not available for free.
Thank you, sir.
Okay, Malesh, anyway, it's nice meeting you at least online after a long time.
Oh, thank you. I am blessed.
Professor
Yes, sir. Sir, you said in one slide that gas in a container splits into two halves. I didn't understand what.
Oh, sorry. It's the container which is split into two halves. It's called a partition.
Oh.
And the gas is either on one side of the partition, and then we make a hole and it comes out, or maybe it's on both sides of the partition. Or even if it was on one side, after sufficient time, it fills the whole container. So our common experience tells you that this is irreversible.
You have mentioned, still it is there on this slide now, that black hole has entropy of 10 raised to 76. How is it because of the quantum mechanical idea this figure has been...
Completely. Because this formula itself contains Planck's constant.
Yeah, Planck's constant.
So the area has to be measured in units of this gh bar over c squared. So it's completely a quantum effect.
Is it a theoretical concept that it is of the order of 10 raised to 76 or...
No, it is theoretical. No one has gone and measured the entropy of a black hole. But for consistency of the whole theory, if you have interactions between black holes or interaction with a normal thermodynamic system with a black hole, and if you want to preserve the laws of thermodynamics, you need to. It's also true that some of the string theorists will be able to calculate this entropy, but for certain models of black holes. So that's why I said it's not that people are completely ignorant of the microstates. In certain specific models, people do compute it.
Sir, to our viewers, Professor Rajaram Nityananda is our life member, Karnataka Physics Association life member. Therefore, we have to congratulate him becoming a life member of our association.
Thank you.
And of course, he has started from basics, and usually in our YouTube, the students are watching this. And I hope that the students would be able to understand the basics of entropy, because he has nicely presented even the basic concepts also. So from Karnataka Physics Association, we thank Professor Rajaram Nityananda. Of course, he, with all his busy schedule, and only in a matter of 2-3 days, he accepted our invitation to give a talk. And we are very happy that he has agreed and given the talk today on basis of entropy. Thank you, sir. And some invitees are also there. That's what I am able to see. From Karnataka Physics Association, we thank invitees and also our KPA members, and Professor Dr. M.K. Raghavendra. He is also here. He is providing the Zoom platform every Sunday, and even his sisters are all helping us to conduct this program. And of course, Raman, S.V. Raman is providing us the YouTube. And of course, many students are actually watching through YouTube. And I don't know whether any other person is available. Anyway, from Karnataka Physics Association, we thank all the viewers, guests, and our own life members. Thank you very much, sir. I think Professor Cogley has to say something toward the end.
No, I just want to thank all the participants of this seminar, and hope they will come back next week for another seminar at the same time. And thank you very much. Now